All right, let's dive into a real classic today. We're going to tackle a problem from a book that has challenged physics students for generations. Irodov's Problems in General Physics. If you know, you know. We're zeroing in on problem 1.199, a really elegant question about what makes an orbit stable.
So, here's our game plan. First, we'll lay out the problem just as it's written. Then we'll put on our detective hats and pull out the hidden clues. After that, we'll review the basic physics, build our equation, and then we'll get to the real heart of it. What does it mean for an orbit to be steady? That's going to lead us right to the answer.
Okay, first things first. Before you can solve any problem, you have to really understand what it's asking. So let's take a look at the exact wording from the book.
So it says a particle moves in a plane under the action of a force, which is always perpendicular to the particle's velocity. And that force depends on distance as 1 over r to the n. The big question is, for what value of n is the motion in a circle steady? You know, with Irodov's problems, the language is always so concise, but there's a ton of physics packed into every single phrase.
I know, at first glance, it can seem a little intimidating. But trust me, we're going to unpack it piece by piece, and you'll see how it all fits together. The trick isn't just about memorizing formulas, it's about learning how to read the problem itself.
So, let's start by being detectives. We're going to dissect this problem statement and pull out every critical piece of information Irodov has given us.
I see 4 huge clues here. Number 1, the force is always perpendicular to the velocity. That's a massive hint. 2, we're told exactly how the force behaves with distance. It's proportional to 1 over r to the n. 3, we know the particle is moving along a circle. And 4, maybe the most important and tricky word in the whole problem, steady.
Okay, before we even touch an equation, let's focus on that first clue. What does it actually mean physically when a force is always perpendicular to velocity?
Well, that's the very definition of a centripetal force. And here's the key takeaway from that. A force that's perpendicular to the motion does 0 work. And if no work is done, you can't change the kinetic energy. So this force can't speed the particle up or slow it down. All it can do is change its direction. It's a pure turning force.
Okay, concepts are in place. Now let's translate this into the language we use to solve things, math. It's time to build our main equation for this system. We're going to start with the GOAT, Newton's second law, F equals ma. Simple enough? Since we're moving in a perfect circle, we know what that acceleration has to be. It's the centripetal acceleration, v squared over r. We just plug that in for a. Then the problem told us the force is some constant, let's just call it k, divided by r to the power of n. So we just set the two sides equal, and there it is. That's our equation for this circular motion.
And right here is where so many people make a mistake. You get this equation, and you think, great, I'm done. But hold on. All we've done is describe what it takes to be in a perfect circle. We haven't even touched that keyword, steady. We haven't checked if this orbit can actually survive a tiny push.
This is the absolute core of the problem. In physics, steady isn't just about moving along a path. It means that path is a stable one.
So we have to ask ourselves this question. Let's say our little particle is cruising along in its circle. What happens if we give it a tiny nudge outwards? Just a little push. Does it fly off into space, or does something pull it back? The answer to that question is the difference between stable and unstable.
The best way to think about this is the classic marble analogy. A stable, or steady, orbit is like a marble at the bottom of a bowl. If you push it up the side a little, gravity pulls it right back to the bottom. There's a restoring force. An unstable orbit is like balancing a marble on top of an upside-down bowl. The tiniest nudge, and it rolls off farther and farther away, never to return. We are looking for the marble in a bowl situation.
All right, this is it. We've got our equation for circular motion, and we have our concept of stability. Now we just have to put them together to finally figure out the deal with n.
So here's the logic, and it's super important. Imagine we nudge that particle out to a slightly bigger radius. To be stable, the actual inward pulling force that's available at that new spot has to be stronger than the force that's simply required to keep it in a circle there. It needs that extra little bit of pull to tug it back to its original path. Think of it like a cosmic tug of war. To stay in a circle at any radius, you need a certain amount of centripetal force. That's the mv squared over r part. The force field itself, though, provides an available force of k over r to the n. Now, for the perfect circle, these two are balanced. But for stability, if r gets a little bigger, the force the field provides has to be more than what's now required.
Essentially, the pulling force can't weaken too quickly as you move out. When you write this down as math, it becomes a simple inequality about our friend N.
And when you work through that math, this is what you get. The condition for stability is just N has to be less than 1. So simple.
So what does that actually mean? Well, think about it. If N is 0, the force doesn't change with distance at all. That's a stable orbit. What if N is negative? Then the force actually gets stronger the farther you go out. That's definitely going to be stable. It's like having a super strong rubber band.
So we found the answer, N is less than 1. But in physics, we never just stop at the answer. We have to ask, what's the story here? What is the physics telling us?
And here's the punchline. For an orbit to hold together, for it to be steady, the force pulling the particle back to the center can't fade away too fast as the particle strays. If the force weakens too quickly, like gravity does, where N equals 2, a particle that gets nudged outward just keeps on going. The leash isn't strong enough to pull it back. The orbit is only stable if that central force holds on tight, if it weakens slowly enough to always be able to pull a wandering particle back home. And that, right there, is the beautiful physical intuition behind this classic Irodov problem.